Hello. In this section, again, we're continuing our work with inequalities. Now we're going to look at quadratic inequalities, right? So this is an inequality, a quadratic where ax plus bx plus c, right? A general quadratic. But instead of equaling zero and solving it like we looked at previously, now we're going to look at inequalities. So if it's greater than zero, if it's greater than or equal to zero, if it's less than zero, or indeed less than or equal to, right? So it's an inequality, okay? And last time we looked at linear inequalities, so like a linear equation. So like 2x plus 5, for example, greater than 6 or something like that. We looked at how to solve it and what that means, right? So now we're going to look at quadratic inequalities. So if we have, say, like some sort of quadratic graph that looks like this, right? Any given quadratic like that. When we say that this quadratic is less than zero, well, what we've done here is plot the curve, isn't it? We plotted the curve y is ax squared plus bx plus c, okay? A general quadratic, I don't know what this quadratic is, I'm not interested in exactly what it is, I'm just for demonstrating. But this is the curve, right? This is the curve of a quadratic, which is this form, right? So y equals ax squared plus bx plus c. Now, if we're saying that this is less than zero, say for instance, right, if it's less than zero, um, well, because y equals this, well, what we're saying is when we plot this quadratic curve, if we want it to be less than zero, well, we want y to be less than zero, isn't it? And y is just the y-axis, right? So y here and x here. So basically, if y is less than zero, what we're interested in is when the curve goes below the y-axis, when y is negative. So the negative y-axis right down here, okay? Or in other words, below the x-axis, right? Because then that's the value when indeed y is less than zero, right? So the y coordinate is negative or whatever you want to call it, right? So we're interested in when the curve goes essentially beneath the x-axis, right? Um, and that'll be again when y is less than zero. So if we then sketch the graph and then we're interested in y is less than zero, we're interested in the part of the graph where again falls below the x-axis. Um, so where's that going to be then in this example? When it's below the x-axis, when y is negative, right? It's going to be this region here, isn't it? Right? That's going to be below the x-axis when y is negative, right? So that is the region we're interested in. Okay. So with that in mind, then we can use that. We can use the graph to solve this inequality here, right? Because remember, when we solve an inequality, we ultimately want x to be less than some number, right? Or x greater than some number, or x less than or equal to, or vice versa. But if you're not solving an equation, is you want x to equal something, right? That's ideally what we want to solve. It's the same with inequalities. Remember, we looked at the last section. When we solve an inequality, instead of x equal a number at the end, we want x to be less than or greater than something, right? So what this is telling us is essentially well the region here we're looking at, right? Um, we want to solve it, the inequality, the x values where the curve is below the x-axis. Okay, so when does the curve dip below the x-axis? Well, it's going to be this point and this point, isn't it? Because then at this first point, right, is when it first goes below the x-axis. Then it comes back upwards at the second point here, and then it goes upwards, but then it's above the x-axis. So when y is positive, okay. So that if when y is positive, that'd be y greater than zero, but we want y less than zero in this instance, okay. So the points we're interested in is the points between 1 and 2, okay. Well, the point 1 and point 2 are the roots of the curve, isn't it? So say if the roots were x is minus 2 here and x was 3, again as an example, well, Then the values when the curve is below the x-axis, when the curve is less than 0, well, that's going to be between when x is between -2 and 3, and it cannot be equal to -2 or 3. It's a strict inequality. It's not less than or equal to. Why? Because if it was equal to -2 or 3, then the curve would be equal to 0, because the -2 and 3 are the roots of it. So that would be equal to 0 at those 2 points. But it wants it to be less than 0, so strictly less than, so not equal to. If it was less than or equal to 0, then actually yes, we'd then have to mirror that inequality by making it less than or equal to here. Okay. But in this case, we have less than. So that is generally the strategy, okay, is to sketch the quadratic, which we know how to do. We looked at in the last section. And then you use your graph to aid you to see where the curve goes below 0. So when it goes below the x-axis, or when y is below 0. However you want to phrase it, okay? But yeah, so that's one example. But alternatively, you could have instead the other direction is greater than 0. It could be greater than 0 instead, okay? Well, I'm gonna stick with this example again. So again, I'm not given the curve. I'm just giving a sort of like and I'm not being specific with the details, right, of what exactly the curve is. I'm just giving the general shape of a quadratic curve. But anyway, okay, we have the same curve again. Now this time, again, it's the same points 1 and 2, but I'm not going to label that here. When that's x is -2, and then the other the other root is x equals 3. Okay, so this time I want, again, if the curve is y equals to this quadratic, and it's greater than 0, well, I want y to be greater than 0, right? Well, this time it has to be on the positive y-axis up here. So it has to be where y is positive. So that will have to correspond to when it's above the x-axis, right? So this is x and that's y, um, the x and y-axis. So if y is greater than 0, well, that means y has to be positive. So we're interested in when it's above the x-axis. So that's going to be this region here. So imagine the curve will extend upwards. It will keep going on and on forever, right? Um, like so. And it got I obviously wouldn't have had to sketch the whole curve because it goes on for infinity. Um, but then it'd be the parts where the curve is it's above the x-axis, right? So it'd be these two regions here. Okay. So hopefully you can see that it's between. So the region I'm shading here is all the distance, if you will, or the region where it's between the curve and the x-axis, so it's above the x-axis. Okay, those are the two regions. So what x values? Again, mark these two regions, and it's going to be the same two x values, right? But this time, instead of it being between these two x values, if it was between, it would be under the curve like this. It's actually firstly going to be less than -2, because if x is equal to -2, it's here. But then we want all the values to the left, right? Because that's where the shading is happening, right? If you imagine, if you go shading forever towards infinity, it would actually be simply all the values of x less than -2. But also on the flip side, we want it to be greater than 3. Okay, I know and we say or. Okay, so you could have it could be one or the other. But either side, if you do it to the left or the right side, the left or right region I've shaded, both of those will, at the end of the day, be above 0, be positive. So y would be positive, so that would be good. And that would be your solution in this case, right? If it was greater than 0, then your roots, you want it to be to the left of the, how do I describe this? Either side of the roots, right? So that's to the left, this side, and that's to the right, that side. Okay. Cool. And there we are. So that's essentially it, right? Just a visualization. Yeah, that's really it. So the whole idea is how we're going to solve these quadratic inequalities is we're going to sketch the graphs, find their roots, which will be part of the graph. Then we can use that to see whether it's below the x-axis or above the x-axis, depending on the inequality. Anyway, let's have a look at some examples then. So firstly, it's saying find the set of values of x for which 3 minus 5x minus 2x squared is less than 0. I don't like negatives and with dx squared. So what I'm going to do is I'm going to just divide or times by -1 to make the coefficient positive. So that'd be -3 plus 5x plus 2x. And remember, when we times it by negative, we have to flip the direction of the inequality. So it would then be greater than 0. Okay. X squared. I'm gonna rearrange this a bit. I want the x squared bit first. I just find it easier to read. So we get 2x squared plus 5x minus 3 is greater than 0. Okay, then now we need to sketch the graph because imagine we call this y equals to this, right? We want to sketch the graph. So uh, to help us sketch it, well, firstly we can note the y-intercept when x is 0. That's going to be -3. Um, but actually you don't need that. But I'm going to call it -3 there. But then we need the roots, okay? Because the roots are pivotal to working out where we're interested in, the regions we're interested in. So to find the roots, well, we just make it equal to 0, right? So then we solve it that way. We know to solve it, we can use quadratic formula. So the roots would be x. And what we don't call them roots because we're not actually solving an equation because it's actually greater than 0. We're not solving equal to 0. What we just call it in this case is not the roots, but we call it the critical value. Okay. I'll write that here. Critical value. So the critical values are the roots of an inequality. Okay. Because again, it's an inequality, not an equation, so they're not technically roots, even though you are solving it in a way. Anyway, we call them critical values. I'll explain why they call that in a second. So then it's exactly the same way. The critical values are going to be equal to, well, we can use the quadratic formula to solve it, right? So we're going to have minus b, which should be -5, plus or minus the root of b squared, which would be 5 squared, -4, lots of 2, lots of -3, all over 2 lots of a, so 2 lots of 2. And then you put that in the calculator, you will get you get x to half, or x is -3. Cool. Okay, so we can plot them as roots. So that'll be here for half, and -3 will probably be about there. If we know the y-intercept is down here, then we know it's going to look a bit like this, right? The quadratic curve. Okay. So we plotted the curve. Um, so, okay, what this is saying is then we want this to be greater than 0. Right, that's the direction in the inequality. We want to be greater than 0. Well, that means we want the positive y-axis here. So we want it to be above the x-axis, right? So we want all the parts of the curve where it's above the x-axis. So up here, not down there. So all the parts above. So it's going to be here, isn't it? It's going to be to the left of this root and again to the right of this root there. Okay, so those are our two regions. Now, I did mention these are called critical values, which are the sort of the roots of an inequality. Um, Now they're called critical values because actually these regions have a fancy name. They're called critical regions. Okay, and critical regions are basically regions or basically solutions of an inequality, essentially. So in a way, like with linear inequalities, we looked at last time, if we had x was greater than 2, we could draw the number line, right? Looking like this, we looked at that last time. Technically, this, the whole like space after 2, think about this as an x-axis, if you will. That's also called like a critical region, right? That's the region that basically satisfies the inequality. Okay, so we call that a critical region. So the particular region or the region of numbers or the region or an area that satisfies an inequality. That's all it is. That's a critical region. Therefore, the critical values are basically the end point or the boundary points of the region. So, for example, the region starts here at the root x is a half. Likewise, this critical region here starts at, well, it is bounded by this root here, x is -3. So remember, that root's -3, and this root is x is a half. So x is a half is the critical value for this critical region there, and x is -3 is the critical value for this critical region here on the left. Okay, so that's all it is. Critical region is the solution to an inequality. That's all it is. So that is the solution to the inequality because it's the region or the area where it is greater than 0. The y value is greater than 0 or it's above the x-axis. Okay. Anyway, so that's the notation we use. So that's the critical value. So then, well, then we found the critical region because that's when y is greater than 0. Well, again, that means if firstly the first region here to the left, that has to be to the left of -3, so it's going to be x is less than -3. Then to the right, the right region here, well, it's all the values when x is greater than a half. Okay, so that's our solution then. Okay, so it's either x is -3, or I should probably say or here, or x is a half. So what that means then, if you plug in any value that's less than -3 or any value that's bigger than a half, if you plug that into this quadratic expression here, you will always get a value that's less than 0 or negative, right? That's the whole idea of this, right? Okay, cool. Um, so let's have a look at another example then. So example 10. First of all, it says find a set of values for x for which 12 plus 4x is greater than x squared. So I need the inequality to be 0. Like with a quadratic equation, we want the equation to be equal to 0 before we can solve it, right? Before we can use the quadratic formula. Exact same mechanism here. We want this inequality to fundamentally be some less than or greater than or whatever, as long as there's a 0 on the other side. But this time we have an x squared, so all we can do is just move it to the left. So if you subtract x squared, we get minus x squared plus 4x plus 12 is greater than 0 now. Cool. I don't like the negative, so again I could just times by or divide through by minus, but divide through by -1. So that'd be x squared minus 4x minus 12. And then we flip the inequality because if we're dividing or multiplying by a negative, we have to flip the inequality. There we are. Then I can solve the, well, I need the critical values then, not the roots, but the critical values, which are basically the same thing. And really, you don't need to be that detailed. But the critical values, again, from solving it equal to 0, um, I'm just going to do the critical value, the quadratic formula, sorry, to get that. So that would be minus 4, so plus 4, plus or minus the square root of b squared would be minus 4 squared, minus 4 lots of 1 minus 12, over 2 lots of 1, and then you put that in the calculator. The critical values are Uh, do, do, do. X is 6 or x is -2. So those are the two critical values, right? Okay, now we need to sketch the graph to help us visualize where the regions will be. So the roots are 6 and -2. Now you can plot the y value to add more detail, but actually, because we know this is a positive quadratic, remember, because the coefficient of the x squared is positive, and with these inequality questions, you can always make the x squared coefficient positive, because like in this instance, we have a negative, but you can just simply divide by you can just flip all the signs, right? Divide or times through by a -1 to simply flip all the signs to get a positive x squared. So this is positive, so you should know that I have like a smiley shape. We discussed this when we looked at a sketching quadratic graph. So it's going to look something like, a bit ugly, but something like that, right? It will look like a quadratic like that. Okay, and obviously we'll say the y-intercept will be -12. So that would be where it passes, but we don't need that detail. Anyway, so we've got a rough sketch. We've got the key details, so where the roots or the critical values are. So what we want this time is when it's less than 0. That means y is less than 0, which means it needs to be below the x-axis. So when it's below the x-axis, so x is here, y is there, the axis is going to be this region, isn't it? Okay. Now hopefully you spot this region this time is actually sandwiched between the two intercepts, the two roots, right? Or technically critical values. So -2 and 6. So so it's between it. So it's going to be between minus. So the x values then is between -2 x and 6. And there we are. Nothing more to it, right? So that's the x value. Remember, again, these are called critical values because those are the boundaries. So this whole region is a critical region, remember. Um, and so the boundary points of the region, so the endpoints of the region, are these two values. And again, that's why they're called critical values because those are the values that mark the boundary or the endpoint of the region that satisfies the inequality. Anyway, I'm just trying to get you used to the language, the terminology. But there we are. So that's the solution, right? There we are. Cool. Okay, that's part A. Then part B then says hence exam tip means you need to use it of earlier part of the question to help you answer this one. So hence one set of values for x, which this inequality 12 plus 4x greater than x squared. Well, hang on, isn't that just the inequality we solved in part A? Yes, it is. So we already got the answer to that. But it says and 5x minus 3 is greater than 2. So we need to solve that inequality as well. Okay. So 5x minus 3 is greater than 2. So then 5x on its own would be greater than 5. So x is greater than 1. Cool. So that's the solution to that. Now we also looked at last time when we have multiple inequalities and you need to combine them. So two different inequalities and you need to solve them together. So this time it's saying and. So that means the x value has to satisfy both the inequalities. So x is greater than 1 and this inequality word out part A -2 x and 6. So think about in words what this is saying. This number x has to be bigger than 1, but also x has to be between -2 and 6. Okay. Well, actually, if we combine them, then this is saying x has to be bigger than -2, but it's also saying x has to be bigger than 1. So overall, x has to be bigger than 1, and then x has to be less than 6. Okay. So that is the overall final solution to that. And again, you can use a number line to plot these inequalities. So firstly, we had x bigger than 1, so x is 1 here. So you have that inequality that way. Then we have minus x is between -2 and 6, so -2 stays here, 6 is there. So it would have to be uh, this line here. And then a solution to both inequalities, again, it's both because it has to be and, so both inequalities have to be true. We want the overlap, which should be here, right? And that occurs when x is 1 here, and then the endpoint when x is 6. And there we are. That's where we arrive to that. Cool. Okay. Before we move on, um, I want to go over the calculator again because actually it turns out the calculator, as good as it is, also can calculate quadratic inequalities. Um, and so let's get this up. Let me. There we are. So, how can we use our calculator to solve inequalities? Well, let's go through it. Let's have a look at this example that we just did. Okay, we can check our answer. So, let's go to menu. So, we looked at solving quadratic equations and simultaneous equations using this option, but we can also solve quadratic inequalities by instead going to option B here on your menu. And then it says polynomial degree, so we can solve. It can solve quadratics, cubics, and quartics, which are degree 4. So we want quadratics. We'll only be expected to solve quadratics in this way. So that'd be degree 2. Then, then it gives you these 4 options. And basically, it's just what the inequality is, right? So in this first example, it's less than 0, so you want option 2. So it's strictly less than 0, so we click option 2. So then it'll give you, and then you have to input the quadratic, right? So we can see firstly it's minus 2x squared. Oh, that's minus 2. Oh, there we are. And then we have minus 5x, so minus 5, and 3. So you just have to put the coefficients in. And then what it will do, then chuck out your solution as so. There we are. So this is when x is less than minus 3, or x, or half is less than x. So we got x is less than minus 3. Okay, that's great. But then it says a half is less than x. That's a bit different to our final answer of x is greater than half. But you should know we can reverse the ordering, switch the sides by switching everything around. So x then be greater than half. That's equivalent, okay? That's the same thing. So actually, indeed, our answer is correct, okay? And there we are. So again, with these sort of calculator tips, I'd use it to check your answer, okay? Rather than just do no working and just write down the answer because you'll lose method marks, okay? Um, yes, the examiner will expect your calculator can compute these inequalities, but they will expect working, okay? So use it as a checking tool. Let's have a look at this one. Okay, this example again. So let's go back to our menu. Again, it's going to be inequality, so B. It's a quadratic, so it'd be polynomial degree 2. This time, well, we needed to rearrange it first, didn't we? So we got, let's have a look at this inequality, right? We rearranged it to get this. So minus x squared plus 4x plus 12 is greater than 0. So we want option 1 because it's bigger than 0. So there we are. So again, the coefficient being minus 1. The coefficient of the x is 4. And then we have plus 12. So there we get this inequality of between minus 2x and 6. And what do you know? That's what we got. So again, we're correct. Cool. So there we are. So that's basically how you can use a calculator, right? Just make sure you rearrange it in the right form, because this calculator will only work specifically when your quadratic is like this, right? You have ax squared plus bx plus c, and then you have to mirror, and then it has to be greater than or less than 0. Okay, and make sure you pick the right sign. Okay, so there are 4 different possibilities. Make sure you pick the right one. Okay, cool. So again, just to emphasize, the calculator should be used as a checking tool, so you do still do your full working out, but it's good to verify you actually got it right. You know, unless again, if it says write down your answer, then the examiner just expects you to put it in the calculator, just literally write it down. But most of the time, you'll be expected to show you working. Okay. Um, okay, cool. Let's have a look at another example then. Okay. So in this one, it's saying find the set of values for which 6 over x is greater than 2. Well, this isn't a quadratic inequality. This looks nothing like it. It's reciprocal. How on earth do we solve this? Well, Okay, when we have an inequality like this with a fraction, a reciprocal, remember reciprocal is like 1 over x, right? Some amounts of that. We have 6 over x here, so it is a reciprocal. How do we solve it in this case? Okay, well, it can be quite hard to do it just as it is directly, to kind of like find the values of x when this whole fraction is greater than 2. But what we can do instead is actually well, think about it as an equation, right? Equals 2. How would you do that? You just times both sides by x, wouldn't you? So then you have 6 equals 2x. However, however, the problem we have here is we have an inequality. And whilst I do say treat an inequality as an equation, the one caveat is that when you have a negative, you have to flip the sign. When we're timesing by just x could be positive or negative. We do not know, okay? So what happens is when we times by x, we are not accounting for whether we have to change the sign or not. So we could, if x is positive, it would still be less greater than 2. It would be 6 greater than 2x, right? But if it's negative, well, then it'd have to be less than 2x. Well, how do we know when to change? Well, how do you know if we should flip the sign or not? We don't know what the sign of x is. We don't know. X could be anything. All it says here is x cannot be 0, which makes sense because you can't divide by 0. But it doesn't say x can be positive or negative. So how on earth do we deal with that? How on earth do we know whether to flip the inequality sign or not? Well, how we get around that is, instead of timesing by x, we times by x squared because a square number is always positive. So we do know the sign in that case. So instead of timesing by x, we now times by x squared. Okay, so we're going to get rid of this now. And that's what we're going to do. Okay, so then 6 over x then times x squared. Well, what's that going to be firstly? Well, hopefully you recognize uh, x squared is x times x. And then we divided by an x, so that will cancel out. So you're left with 6x, okay? So overall, you're going to get 6x. And that's going to be greater than, well, 2x, right, be 2x squared, isn't it? Because 2 times x squared is 2x squared. Now we got a quadratic inequality. So I'm going to move, well, well, firstly, I'm going to move the 2x squared to the other side to get it well, not equal to 0, but it has to be 0 at the other end. So then minus 2x squared plus 6x is greater than 0. And again, then I don't like a negative, so I'm going to just divide by minus. Well, I can divide by minus 2 actually, because 2 also goes into all the numbers. So I get x squared minus 3x divided by minus 2. 6 times divided by minus 2 is minus 3. And then we reverse the sign to less than 0. Okay, now we can solve. This is a quadratic, right? So again, as always, we first find the critical values, which will allow us to sketch our curve. Well, critical values, well, that's when this is equal to 0, isn't it? But we can factorize, right? So x squared minus 3x is equal to 0. We can simply factorize to get x minus 3 equals it. Then clear. Okay, so we get the solution then either x is 0 or x is equal to positive 3. So each bracket, each factor equals 0, right? Um, so yeah, so those are our critical values. So then we can use that to draw a graph, right? A quadratic graph, x squared minus 3x. So our roots are 0 here, or 3. So then we can use, so then our graph will look a bit like this. There we go. Okay, there we are. We put that as the root. There's a bit off there, but there we are. So it'd be 3 here or 0. So those are our sort of roots or critical values technically. Okay, so we use that sketch a graph. Okay, then what region we're interested in? Um, so it's going to be this, right? Less than 0. So that means y is less than 0. So the curve y is less than 0. So it's going to be below the x-axis, right? This is x and y. It's going to be below the x-axis. Cool. So then actually you can spot the region then that are shaded, which is below the x-axis. That's going to be between the 2 points, right? So when between x is 0 and x is 3. So there we are. So that's the solution there. Cool. And so yeah, hopefully you spotted what did there again. Just to recap. So we solved the inequality to start off with. By well, we kind of treat it like an equation, right? If it was equal to 2, we would just times by x, but we times by x squared instead to incorporate the fact that we needed a positive number to preserve the inequality sign, right? So instead of times by x, we times by x squared, okay? So times by the square number, okay? To then keep it positive, and then that allows us to solve this equation. Cool. And then we used to solve the quadratic inequality like normal to then find the critical values, and then we sketch the curve to find the region which occurs at these x values. So that's the values of x. Okay, cool. Then I've got two more questions to look at. So it says first, it's a very similar example. Then, given that x is not 3, find the set of values for which 5 over x minus 3 is less than 2. So let's write that down. Again, if I were to solve it as like a normal equation, if it was equal to 2, I'd be times by x minus 3, right? Cross multiplying, if you will. However, I have an inequality, so I can't just times by minus 3 because x minus 3 could be negative or it could be positive, right? Again, so how am I going to account for that? Well, I'm just going to times by x minus 3 squared, okay? So then 5 x minus 3 squared over x minus 3 equals 2 lots of x minus 3 all squared. Well, what I notice is these are 2 lots of x minus 3 here, so one of them will cancel with that. So I'm simply left with 5 lots of x minus 3, but it's not equal to, it's less than. And that'd be less than 2 of x minus 3 all squared. So that's what I've done there, right? So times by the denominator like you'd normally do with a fraction equation. But because we have an inequality, we need to times by the x minus 3 squared, because then that's a positive number. That allows us to maintain the inequality. Okay, and again, I'm times it by x minus 3. That would be adding a solution x minus 3 equals 0. But x minus 3 cannot be 0 because x cannot be 3. If x was 3, then 3 minus 3 would equal 0. That means the denominator, the fraction, wouldn't exist because the denominator was 0. So I've not added. I've not done anything wrong there. So yeah. So that's the whole method, right? Times by the denominator squared. Okay. Okay. So let's go on. Proceed. So we can expand the bracket. So we're gonna have 5x minus 15 is less than 2. And then we're going to expand this bracket. So x minus 3 squared is x minus 3 times by itself. So that's going to be 5x minus 15 is less than 2 lots of, and then we'll expand these two brackets of x squared minus 3x minus 3x minus 6x plus 9. Then I'll expand that to get 5x minus 15 is less than 2x squared minus 12x plus 18. Then I'm going to move, I'm going to move all this to the right side because there's a lot more, this to the right side. There's a lot more stuff on the other side. So I'm going to get 0 is less than 2x squared. Take away 12x, take away 5x, take away 17x. Add 15, add 18, you get plus 33. But then I can simply just reverse the ordering, right? I can switch the sides around to get simply 2x squared minus 17x plus 33 is actually greater than 0. Okay, and there we are. So now this is a quadratic to solve. Um, so then I need the critical values, and these are x is equal to, I'm going to do the formula, so it's going to be 17 plus or minus square root of 17 squared minus 4 lots of 2, 33 over 2 lots of 2. So if you do that in the calculator, you get x's 11 over 2, or x is 3. There we are. Cool. So there we are. So that's our two critical values. So again, if we were to sketch the curve, let's sketch it here then. Again, so 11 over 2, which is 5.5. So 3 is going to be first, and then 11 over 2 is going to be there. So then the curve is going to look a bit like this, right? And there we are. So that's 11 over 2, and that's 3. That's the x values. Okay, so okay, then it's saying again. Let's look at the inequality then. What region or where on the graph are we interested in? So it's going to be greater than 0. So that's going to be above the x-axis, right? So if we were to continue this on, that'd be x. That'd be 11 over 2. So above the x-axis is going to be actually the part of the curve above it. So it's going to be these regions, right? There and there. Okay. And obviously that would go on forever because the curve actually would go on forever, right? So actually it'll go towards infinity. So those are the two values. So actually the first region on the left is the values when x is less than 3. Or the other region is when x is bigger than 11 over 2. Okay. So when x goes that way to the right. So those are two solutions then. There we are. Cool. And obviously you can check your answer. You would be able to put this in the calculator because a calculator only works when your inequality looks exactly in this form here of a quadratic less than 0, greater than 0. If you put that in your calculator, then hopefully you should get these two values, these two inequalities. But again, make sure you show your working. Okay. Okay, cool. So hopefully you see what we do there, right? To deal with a fraction inequality, you can just times by the square, okay? So the denominator, like you normally do, but you square it instead, because then that'd be a positive number. Cool. Final question then. And this is quite a classic exam question, actually. But it's saying then that this equation, kx squared minus 2kx plus 3 equals 0 has no real roots. Okay, so this is an equation equal to 0. It has no real roots. So that's talking about the discriminant, isn't it? So we know that when it has no real roots, the discriminant b squared minus 4c has to be less than 0. Okay, has to be negative. Well, there we are. Then it's asking to show this. Okay, show that k satisfies this. Okay, well, we don't roughly know how to get there, but what we can do is just work with this information. This is an inequality, right? That might help us. So just work with what we know, work with what we normally do. So no real roots means the discriminant's less than 0. We've seen it loads of examples like this in the previous chapters. So just put the discriminant in, okay? Even if it has a k in, just work with it, right? So b squared will be minus 2k. So b is minus 2k, the coefficient all squared minus 4 of a, which should just be k, and then c, which is 3. And that's less than 0. Cool. Then we just square this, get 4k squared minus, minus 4 times k times 3. Minus 4 times 3 is 12, so that would be minus 12k, less than 0. We can divide by 4 to make it easier for us. Don't have to, but then that'd be k squared minus 3k less than 0. And then this is just a quadratic inequality, isn't it? So then we need the critical values, which again is when you equal it to 0. So that's going to be, well, we can factorise it. So k squared minus 3k is equal to 0. That's where we get our critical values. So then k of k minus 3 equals 0 by factorising. So simply set each factor, because this is a factor, so I'll remember a k outside, but then that'd be k equals 0 or k equals 3. So those are two critical values that allow us to sketch the quadratic. Let's draw it down here. So then that's going to be, well, the roots of 0 here and 3. So it's gonna look a bit like that, okay? Noting again, it's a smiley shape because it's a positive k squared, okay? If you divide by an if you always you can always again I talked about this earlier, but you can always make the quadratic positive by just simply dividing by negative if it is a negative. So it should always end up with a U shape, right? Um, if it's a negative, then again you'd have to just spot where the region is that you're interested in. But you can always make it positive, so you don't need to worry about that. Anyway, so that's our shape. So what region we're interested in? Well, it's less than 0. So that's going to be below the x-axis. Okay. Well, actually, it'd be k, not x, because it's k now, not x for solving. Uh, but it's going to be below the axis this time, so it's going to be less here. That'll be when y is less than 0. Well, then the solution is actually between the two values, between the two roots, if you will, right? So it's between this first root 0 and the second root of 3. So it's between the k is between 0, k and 3 to get this inequality, and there we are. Okay, so we've got this inequality. So that's our range of values for k. So let's have a look at the answer. So it's between 0, k, and 3. Okay, great. However, there's this caveat here, has to be less than or equal to. Okay. And why is that? Well, when you're in this instance, what you can do is it's saying k can also be equal to 0. If you're a bit unsure, just literally plug in what happens when k is equal to 0. Okay, so clearly it's also including 0. Um, so let's just try. Let's see what happens when k is 0. Okay, so if I say when k is 0, just literally plug that into the equation and see what happens. That means kx squared. Oh, I didn't mean to do that. Not k squared, kx squared minus 2kx plus 3 equals 0. That becomes then 0 squared, that will go away, minus 2k, which should be 0 as well. Then you're left with 3 equals 0. Well, hang on, that's not true. That cannot happen. Therefore, that tells you that equation has no roots, okay? That equation is not true. So it has no roots. So actually, it's therefore true. Also, the equation also has no roots when k is equal to 0. So k equals 0 also means equation has no roots. Okay, or no real roots. That's what it said, right? So actually, that means we can actually also incorporate k0 into our solution. We can add that in. So we know k has to satisfy this inequality, but we've also seen that k can also be equal to 0 as well. So actually, our final answer is 0 between 0, let k can be less than or equal to 0, because this is not happens with k is 0, and then less than 3. That is your final solution. There we are. So that's quite an interesting final question, that is. But why is that? Why does that happen? Why is it not just 0, k, and 3? Why? Um, well, what? Think about what happens here then. That's why substituting it helps to see, why it happens, right? So we're seeing it isn't true in k0 when we substitute it in. We get 3, 0, which is nonsensical, so it has no roots. So we know that's also true. But why can't we just not only rely on the inequality here? Well, it's not like the equation is. It's not that the method's fickle. The method will work. What we just looked at. It's not like sometimes it doesn't work. And we don't. That's not what maths is, right? It should always work no matter what. But it doesn't work here. Well, it does work, but we have to consider this extra with k0. We have to add on something else because when k is 0, well, kx squared, the x squared goes away. The equation simply becomes 3z equal to 0. That is actually no longer, well, this is technically 0x squared plus 0x, right? This is no longer a quadratic, okay? Because there's no x squared term. There's no x term either, but there's no x squared term, which means it's not a quadratic anymore. The equation fails to become a quadratic when k is 0. That means that when we're solving a quadratic inequality, it's a quadratic, right? But then when k0 is not a quadratic, because the quadratic term goes away, so this inequality is only true for, well, it's not only, but it's true for every value of k apart from 0, because when k is not 0, then kx squared is defined, right? X squared does exist, right? If kx squared, when k is not 0, then kx squared, say k's got 0.0001, but that's still 0.0001x squared. That x squared exists. But if we had 0x squared, well, then the x squared goes away. So that means we do not, it wouldn't be a quadratic, which means we wouldn't get a quadratic inequality. So that means it wouldn't be part of this solution here. So that is why we needed to consider k0 as well, because of the fact that then that would no longer become a quadratic, um, which means this method, not method, but this answer does not consider what happens when the x squared term goes away, because of the fact that we have a quadratic inequality. So yeah, okay, but that can be a bit difficult to spot, quite difficult. But the question does help you out here. Again, this is an exam tip. If you're close to an answer like this, just test what happens when you put the other values in. I got 0 less than k less than 3, but the answer is 0 less than or equal to k. But what happens when k is equal to 0 then? There might be a reason why that doesn't work, and in this case, we saw it because 3 is equal to 0. That means it's also a solution, okay? So that means we can add that extra solution onto our inequality to get this new inequality. And there we are. But that's the reason behind it, okay? The fact that simply with k0, the equation breaks down, okay? The x squared goes away, so it's no longer a quadratic. And because it's a quadratic as well, when it's not, we told there was an example at the very end of the discriminant chapter when it's a similar concept, but the fact that the x values were limited. So we had a quadratic graph. Remember, it looked a bit like this, but then there was the curve did not continue on like this. So it was limited in x values, which means we couldn't just use the discriminant. What I'm saying that in this case is we have no quadratic when k is 0. That means we can't use the discriminant because the discriminant only works for quadratic, right? So if we have no quadratic, then the discriminant does not apply. And because we've got our inequality from the discriminant, that means that this final inequality we've got here from the quadratic inequality does not consider the fact when k is equal to 0. Because when, again, to reinforce what I'm saying, when k is equal to 0, then the quadratic goes away. There's no quadratic, which means there's no discriminant. So we have to consider that separately, okay? So that's where that comes from. Okay, cool. That was an interesting final question there. But yeah, I'm going to leave that there then. So I'll see you later.